This activity is designed to help us understand what is the span of a set of vectors in linear algebra and make the connection between span and the nature of solution sets of linear systems of equations. Follow along with this activity 233 taken from Austin's linear algebra textbook. In EdPuzzle, you'll see prompts popping up occasionally to respond to. So first of all, let's go back to the actual precise definition of what span means. One of the confusing things about the word span is that in linear algebra we can use it both as a noun and also as a verb. And I'm going to just draw attention to those both usages as we go along. We're going to start with it as a noun and say that the span of a set of vectors, so v1 up through vn are vectors, the span refers to a set. And it's the set of all what? How does that set relate to this set of vectors? It's the set of all linear combinations of those vectors. Remember, linear combination is the operation that makes linear algebra run. And so when we say the span of a set of vectors, it's the set of everything that we can make out of those vectors via linear combination. So using set builder notation, we'll say that it's the set of all linear combinations with the weights C1, C2 up through Cn being chosen from among the real numbers. So it's a set of all multiples of v1 added to all multiples of v2, added to, etc., all the way up to all multiples of vn. And those multiples are all real numbers chosen to range independently over all real numbers. Okay, so that's the precise definition. In this activity, we're going to build up our intuition for what span is, what it looks like, and what it has to do with solving linear systems. First of all, in part A, we're given a vector 1, 2, 1. And we'd like to come up with a written description to describe what is the span of the set which consists only of this one vector. So we want to talk about it, and we want to come up with a rough sketch of it as well. Let's start by returning to the definition. The span of a set consisting of just this one vector is supposed to be the set of all linear combinations of that one vector. We only have one vector to work with here. So it's a set of all C1 times V, where the C1s that I can put here are chosen from among all real numbers. So in other words, this is a set that's going to contain a bunch of multiples of the vector v. 0v, 1v, negative 3v, square root of 2v, pi v. Which of these are going to be included and which ones of those are not? Well, because my multiple, my weight, can range over all real numbers, and all of these weights I've written down here are in fact real numbers, all of those are included in the span. Any multiple of this vector v is going to be a part of my span. So it's the set of all multiples of this v. And if I sketch my v in the xyz coordinate system down here, so its coordinates are 1, 2, 1, 1 out on the x-axis, 2 in the y direction, and then 1 up in the z direction. If I sketch this span, what is the shape of this span, which consists of all multiples of v, going to look like? Well, because when we multiply a vector by a scalar, what we always end up doing is either stretching it in a parallel fashion, if the weight is positive, or stretching it in an anti-parallel fashion, if the weight is negative. What we end up with is a line. We sort of stretch that vector out to infinity in both directions, and that set, the set of all points which are some multiple of this v, will then form a line passing through the origin in 3 space. One of the things that we can do is understand the parameter c1 here as being almost like a coordinate system for the points along that line. When c1 is equal to 0, I get the point here. 0, 0, 0 happens to be at the origin. When c1 is 1, I get the point which is just the vector v. When c1 is 2, I get 2v, 3v, 4v, 5v. All of those points are in the span of v. So is negative 1v, negative 2v, negative 3v. But then remember, my C1s can be real numbers, not just whole numbers or integers. So we get everything in between as well. We get square root of 2v sitting in between 1 and 2v here. We have pi v. We have negative the square root of 5v. All of those points on the in-between. So we really do get an entire line worth of points. And we can think of C1 as being like the coordinate system, which tells me how far and in which direction along this line I'm going. So I had this one vector inside of 3 dimensions. When I took the span of the set that only had that one vector in it, that span is a line, parallel to the vector v, passing through the origin. So that's what happened when there was only one vector in the set of which we were taking a span. What happens if I add more than one? In part B, we're going to look at the two vectors 1, 0, 0, we call it E1, and 0, 1, 0, we call it E2, and ask the same question. how do we describe what the span of the set consisting of those two vectors looks like, and what does that look like inside of the xy plane in a sketch? So first of all, the vector e1, whose coordinates are 1, 0, 0, if I sketch that in xyz space, where is it going to reside? That vector, because its y and z coordinates are both 0, is going to lie right on the x-axis, 1 unit of distance out along the x-axis from the origin. For similar reasons, e2, 0, 1, 0, lies on the y-axis, 1 unit distance away from the origin. So there's e1 and e2 themselves. If I bundle e1 and e2 together into a set, all I get are these two vectors. If I take the span of that set, according to this definition, I'm supposed to get the set of all linear combinations, everything that we can make from e1 and e2 by adding multiples, arbitrary multiples of them to one another. So it's the set of all c1e1 plus c2e2, where c1 and c2 are chosen from among all real numbers, arbitrarily and independently. So if I put in e1 and e2, I can then ask the question, if I were to take c1 times this vector and c2 times that vector and add them together and simplify, what are all of my possible answers going to have in common? When we carry out that arithmetic, c1 ends up as the first entry, c2 ends up as the second, but the third entry, no matter what we chose for c1 and c2, that third entry is going to end up to be 0. And therefore, the one thing that all points of the form c1, c2, 0 have in common is that their z-coordinate is equal to 0. Therefore, what we've got here, since x and y can be chosen to be, well, how do we choose x and y in this set? X and y can be chosen according to the restrictions on c1 and c2, and the only restriction is that they be real numbers. X and y, which are c1 and c2, can be chosen to be absolutely anything. So what we've got is a description of a set in which the x and y coordinates of my points can be anything they want to, but the z-coordinate of my points all have to be 0. Therefore, what I have is a description of what subset in xyz space? That's right, we're talking about the xy plane, the set of all points in xyz space whose z-coordinate is equal to 0, but whose x and y coordinates range over all real numbers. Just like in our last example, we can think of the parameters, this c1 and c2 over here, as being a coordinate system for the span of my two vectors. For instance, when c1 is equal to 1 and c2 is equal to 0, I've got the point e1. That point actually belongs to my span. Same thing for when c1 is 0 but c2 is 1. I get the point e2. But the point where c1 and c2 are both 1, I get the point which is the sum of e1 and e2. So I get this point. If c1 is 1 and c2 is 2, then I get this point, and so on and so on. So my c1 and c2 are giving me kind of a coordinate system for this entire plane, which is the span of e1 and e2. So how is that intuition borne out by the algebra? So we decided that the span of our vectors e1 and e2 is in fact the xy plane sitting at a height of 0 inside of xyz space. So the plane z equals 0. How does the algebra reflect that fact? Well, remember, another way to think about linear combination is exactly the operation that powers matrix multiplication. So, if I were to multiply the matrix whose columns are e1 and e2 by an arbitrary vector x, the result, by definition of matrix multiplication, is that I get a linear combination of e1 and e2 whose weights are given by the entries in the vector x. So therefore, another way to think about the span of a set of vectors is it consists of everything which I can get by multiplying a matrix whose columns are those vectors by any weight vector x that I choose. So anything of the form e1, e2 times x is going to be an element of the span of e1 and e2. So, how are we going to understand this system? How is the solution of this system, where b is some arbitrary vector that I choose inside of 3 space, if I can solve this system, then that means that there are weights that show that b is a linear combination of e1 and e2. So how is this solution going to relate to the span? Well, what would I want to do if I tried to solve this equation? What would solving this equation require? To solve this equation, we would just form the augmented system, with e1 and e2 in the first two columns on the left side of the augment bar, and on the right side is the vector b1, b2, b3. Luckily for us, this matrix is already in its reduced row echelon form, so we don't have to do any row operations to make the following conclusion. How many pivots are there? We can see directly from this reduced form that there are 2 pivots in this matrix. And so this matrix has a shot at being a description of a consistent linear system of equations. But there's a catch. according to this reduced row echelon form, what has to happen in order for this system to have been consistent? In order for this system to have been consistent, this last row, which doesn't have a pivot, has to correspond to a true equation. But the equation that that row corresponds to says 0, on the left side, equals B3. And so that's only going to be a consistent, a true statement, when the value of B3 is equal to 0. Then I'll get 0, 0, 0 in my last row, which is a true equation, and it doesn't screw up the consistency of my system. So this system is only consistent when B3 is equal to 0. But what is the role that B3 plays if the question is, for which B vectors do I have B equal to a linear combination of E1 and E2? My B vector is being chosen arbitrarily inside of 3 space. What's the role of that third coordinate? That third coordinate is exactly the Z coordinate of the B vector that I've chosen. So what this is saying is that if I choose, or if somebody chooses for me, a vector inside of 3 dimensions, then if the third coordinate of that vector is 0, this system will be consistent, and B will therefore be an element of the span of E1 and E2. And if not, if the third coordinate is not 0, then this condition won't hold, that condition won't hold, this system will be inconsistent, and B will fail to be an element of the span. So what's another way to describe the set of all points in 3 dimensions, XYZ space, for which this will be a consistent system? Because the role of B3 is to represent the Z coordinate, an equation for that set of points is exactly the equation Z equals 0, namely the XY plane sitting at a height of 0 inside of 3 space, which is exactly how we described the span a moment ago. So we're beginning to get a feel here for what span does. In our first example, we had a single vector, and the span of that single vector turned out to be this entire line, with the value of this parameter sort of telling me how far and in which direction along that line that we're going. And then likewise, here we had 2 vectors, and in this example, the span of my set of 2 vectors was an entire plane, namely the XY plane, sitting inside of 3 dimensions. And we've just come to appreciate that the question about which vectors belong to the span of a set of vectors is really the same as the question which vectors can be made linear combinations of our set of vectors, which is really a question about the consistency of this associated linear system. So this system is a consistent system exactly when the right-hand side vector B belongs to the span of the columns of my matrix. So in our next video, we'll continue this activity and think a little bit more about the relationship between span and consistency in linear systems. So don't miss that second half of this activity.